If a polynomial has integer coefficients, then every rational solution of f of x equals 0 has the following form: p over q, where p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. So, in order to use the rational root theorem, we do something called the rational zeros test. Use the rational root theorem to find the rational zeros of a polynomial. All possible zeros are in the form p over q. So we'll find all the factors of the constant term and the factors of the leading coefficient in order to create all possible rational zeros. To find the actual rational zeros, we need to use synthetic division to test the possible rational zeros. You may want to use a graph to check which possibilities are most likely. Example 1, find all real solutions of x cubed minus 8x squared plus 11x plus 20 equals 0. So the first thing I'm going to do, I see that this is a polynomial. If I can factor it, that is definitely the easiest way to find the zeros. This is a polynomial with 4 terms, so I would try factor by grouping. Factor by grouping doesn't work because you don't end up with the same group attached to each product. So if we can't factor easily, then we're going to use the rational zeros test. First of all, I need to know what are all the possible rational zeros. The possible rational zeros are in the form p over q. P is all the factors of the constant term. So I want to know what is the constant term, and then I also want to know what is the leading coefficient. P represents the factors of a sub 0. So what are the factors of 20?
1 and 20. 2 and 10, 4 and 5.
But couldn't I have -1 times -20, or -2 times -10, or -4 times -5? Okay, so when you are finding all the p values, you must include the positive and the negative versions. Q represents the factors of 1. That would be plus or minus 1. We found all possible p's, we found all possible p's and all possible q's, so now it's time to... We found all possible p's and all possible q's, so now it's time to make all... We found all possible p's and all possible q's, so now it's time to find the ratio of p over q. So possible rational zeros are in the form of each p over each possible q. So plus or minus 1 divided by plus or minus 1 is plus or minus 1. Plus or minus 2 divided by plus or minus 1, plus or minus 4 divided by plus or minus 1. And you may start to see the pattern here. But if there was another factor in the denominator, that would give you twice as many p over q options. So we found the possible rational zeros. Now it's time to find the actual rational zeros. How do you find the actual rational zeros? You use synthetic division for each of these in order to determine whether each is a zero of the polynomial. So I'm going to use synthetic division to divide this beginning polynomial, which has coefficients of 1, -8, 11, and 20. I'm going to divide it by my first possible rational zero, which is positive 1. For synthetic division, to start, the first one needs to fall, and then we multiply diagonally, so 1 times 1 is 1, and then you'll add vertically. -8 plus 1 is -7. Multiply, add, multiply, add. So how do I know if this is actually a rational zero? Look at the spot here, which is usually a remainder. If there's a number here, then that means it's a remainder and there's no even dividing. But if this number here is 0, then there's no remainder. You've divided evenly, and this would be a 0 of the polynomial. Let's use synthetic division to try dividing this time by -1. First one needs to fall, then we multiply -1 and then add. Multiply, add, multiply, add. Ding, 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 we have 0 as our remainder. If the remainder is 0, that means this divided evenly, which means -1 is one of the zeros of our polynomial. So -1 is a 0 of our polynomial because it fits the factor theorem, that if you plug in k, which in our case is -1, f of -1 is 0 which means x minus k is a factor of f of x. X equals -1 is one of my actual rational zeros, and the factor when x is equal to -1, remember k is -1, so it would be x minus -1 or x plus 1. So this is one of the factors of the polynomial. I'm going to keep adding on to the factors and to the actual rational zeros. But how? I found one. Does that mean I have to test out more of these? We use the rational zeros test because this was not easily factorable. But now the resulting coefficients are of a quadratic polynomial, and we know how to solve quadratic. So what is the resulting polynomial, quotient polynomial here? Well, remember the power is down 1 from what it was before, and it was x cubed to begin with, so the quotient will have x squared as its degree. 1x squared minus 9 times x plus 20. So x plus 1 times this quadratic will give me the original starting polynomial. But this is not fully factored. What you need to do now to find all the other zeros is solve this quadratic. I'm going to try by factoring. X times x gives me x squared. Multiply to get 20 and add to get -9. Oh, that's -4 and -5. So the factored version, fully factored, looks like this. The actual rational zeros would be x minus 4 equals 0, x minus 5 equals 0, so +4 and +5. If this quadratic was not factorable, then I would need to use completing the square or quadratic formula to find the rest of the zeros. Find all real zeros of f of x equals 10x to the 4th minus 11x cubed minus 42x squared plus 7x plus 12. The first thing is I don't actually know how to factor something that has 5 terms in it, so that's why the rational zeros test will narrow down your possibilities. So a sub 0 is 12, a sub n is 10. P would be the factors of 12, and Q would be the factors of 10. Do not forget to include all the plus or minus possibilities. To get my possible rational zeros, I'm going to include all possible ratios. That's going to be a lot. So, first option, plus or minus 1 divided by plus or minus 1 is plus or minus 1. Second option, plus or minus 1 divided by plus or minus 2 is plus or minus 1/2. Third option, plus or minus 1 over plus or minus 5, plus or minus 1 over 10. Now 2, plus or minus 2 over plus or minus 1, plus or minus 2 over plus or minus 2 is plus or minus 1. We already have plus or minus 1, so we don't need to write it again. Plus or minus 2 over plus or minus 5 is plus or minus 2/5. But plus or minus 2 over plus or minus 10 is plus or minus 1 over 5, which we already have here. There are some that are already taken care of. Pause the video and then press play when you've come up with all the P over Q possibilities. This particular polynomial has tons of possible rational zeros, so we're going to enlist the help of a graphing calculator. But if it's a simpler problem, then you won't be given a graph. You'll just need to test out values. The real zeros of a polynomial show up in the graph as x-intercepts. So we're looking for which of our possible rational zeros match up these location of our actual rational zeros. This one right here looks like it could be -1.5. This is -1. This is -2. So it could be -3/2. Let's test it with synthetic division. It might take a little longer, but it's definitely possible to do synthetic division with fractions. Go ahead and try it on your own and then press play to check. So is -3/2 one of those zeros? No, it is not, because we have a remainder. Our remainder would need to be 0 in order for it to be a 0. Okay, so you could try -3/5, -4/5. Those could be a little bit more difficult. I think this might actually, -1/2 might be a 0. That's a slightly easier fraction to deal with. Let's try it. Use synthetic division to test if negative 1/2 is a 0 of this polynomial. Then press play to check. Well, would you look at that? 0 is the remainder, so negative 1/2 is one of the actual rational zeros of this polynomial. Okay, so now you've used synthetic division to actually divide, and your resulting polynomial is 1 degree less than the original. That could break it down and make it possibly factorable, so this should be 10x cubed minus 16x squared minus 34x plus 24. Now I have a cubic polynomial. It has 4 terms, so I always check to see if I can factor by grouping. But before I even do that, always, first and foremost, is there a greatest common factor? Is there a GCF in each of these terms that I can actually reduce? Yes, 2 goes into every single one of these terms. I can factor out a 2 from this polynomial. Can you factor that by grouping? Yeah, it doesn't look like those will give you the same groups. So the only other way I know to solve a cubic is to try to find the possible rational zeros and then narrow it down using synthetic division. So that's what we'll do. Now we have a new polynomial. Let's use the rational zeros test. A sub 0 is 12. A sub n, in this case, is 5. P is all the factors of 12. Q is all the factors of 5. P over Q is the form that all possible rational zeros come in. Be sure to include every P over every Q. Then press play and check. That's a lot of possible rational zeros, so we're going to use the graph to help us narrow it down. This 0 looks like it's about a little bit more than 1/2. Which option here is a little bit more than 1/2? The fraction that's close to but a little bit more than 1/2 would be positive 3/5. So we're going to test that out with synthetic division. Yay! We have found one of the zeros of this new polynomial. So we can add 3/5 to the list of actual rational zeros. Now we found a 0 of the cubic polynomial, so the resulting quotient polynomial is quadratic. This should be 5x squared minus 5x minus 20. Notice how there is a common factor between all 3 terms? 5 actually goes into all of these. Now I have an even simpler quadratic equation to solve. Is this factorable? No, it's not. So you can use complete the square or quadratic formula. I'm going to use quadratic formula so I don't have to deal with fractions. Press pause, do the quadratic formula, and press play to check. These are the last 2 zeros. They had an irrational in them. It was 1 plus or minus root 17. So root 17 is an irrational number. And so that is not a rational 0, that is a real 0. All the zeros we found were real, but only the ones that can be written as a ratio are rational. But it's still a real 0 because it does not have the imaginary number. Negative 1/5 and 3/5 are also real zeros. So my factorization was x minus my first 0, x minus the next 0. We factored out a 2 in this step, and we factored out a 5 in this step. So 10 needs to be multiplied by the quadratic that gave you these real zeros. The only thing is, when we factor, we don't usually get these weird fractions. And so, to write them as non-fractions, which is a helpful piece of information, if x equals negative 1/5, then x plus 1/5 could be 0. Or I could multiply both sides by 5 and then add 1 to both sides. 5x plus 1 is the same factor as x plus 1/5 because it results in the same 0. So instead of writing x plus 1/5, I'm going to write it in its non-fractional form, 5x plus 1. How would we do that for x minus 3/5? Well, that's x equals 3/5, and I'll multiply both sides by 5. So we've turned this into a non-fractional factor. And the final quadratic is not factorable. They didn't ask for the factorization, but I wanted you to see how a fractional zero shows up in factorization. And the real zeros that we needed to find were here. There are 2 answers here and 2 answers here. And that means we found all the answers we need to because we started off with an x to the 4th.